Hello everyone. So my name's Cate Macinnis Ng. I'm a new lecturer at the School of Biological Sciences at the University of Auckland. I've just done 2 weeks on the job, but before that I was a senior research fellow in the School of Environment, also at the Uni of Auckland. So we've been working on this project for a number of years now, since 2011, and I'm going to talk about this ongoing work that I'm doing with my PhD student, Julia Kaplik, who's in the audience today, and I'd like to acknowledge my other collaborators, Mike Clearwater at the University of Waikato, and Lugard Schwendemann, who's also at Auckland with me. So I'm going to talk about another way that plants can die, but I'd like to let you know to begin with that this is a good news story for kauri. So we all know that if we withhold water from plants for long enough, they will eventually die. But some plants can last longer than others. And that's because plants have different sorts of processes or adaptations that allow them to deal with dry periods. And as plant physiologists, we like to put the plants into boxes, and we can define what type of drought strategies they have to help them get through dry periods. And what I'm going to show you today is that kauri have a number of different strategies they can use that means they can be classified as drought avoiders. So what I'm going to do is talk you through these different processes or features that the plants have that allow them to cope when the soil is dry. Now, it's often said in the literature that kauri are drought robust and they're able to cope with drought, but there's also some evidence to suggest that they may be vulnerable to drought. And the first piece of evidence is something that's come from a paper from the 80s that talks about the fact that in some timber appraisal reports around 1917, there was a report of, around 1926, there was a report of dead kauri because of the 1917 drought. And so it's quite early on in the literature that we can find references to kauri being impacted by drought. But I will say that that's not really well established that it was the drought that caused these dead plants to be there. Something that's much better supported is the fact that we can talk about kauri as being highly vulnerable to xylem embolism. Now, this is a phrase that just means that when drought occurs, air bubbles will form quite easily within the xylem or the conducting pipes of the plants. So when there's not much water in the soil, plants start to sort of have this loss or breakdown of their water conducting systems. And for kauri, this happens when the soil is not too dry at all. So this means that if only a very slight drought comes along, they're really vulnerable to drought effects. Another piece of evidence is the fact that they may have shallow roots. So some of the literature refers to the fact that most of their fine roots are close to the surface, and so as a drought progresses, the surface dries out fastest, and if a tree doesn't have access to deeper water availability, then it may be really vulnerable to drought. So this shallow roots thing, there's a couple of papers that refer to it, but it's not really been properly established. And then finally, the remaining kauri exist on ridgetop locations, and this means that they're really exposed, and as a drought happens, there's a lot of runoff, so there's not water collecting on those ridges. So a lot of evidence there that kauri may be drought vulnerable. And this is what some of the things that really motivated me to look into this work. And of course, there's a lot of interest in kauri, and the 2013 summer drought, we saw some media coverage looking at what that meant for the kauri and what should happen. And if we look at climate change scenarios and modelling, kauri exist in Northland, which is one part of the country that's really going to become drier. So not only will droughts be more frequent, but they're also likely to be more severe. So with that in mind, it's really important that we get an understanding of what drought means for the kauri. So I set up an experiment at the Huapai Scientific Reserve. This is a piece of land belonging to the University of Auckland. It's a remnant piece of vegetation that has some older kauri and also some rika kauri in it. And so this site's really accessible especially for scientific research. And we started the work in July 2011, and it was still ongoing when the summer drought arrived in 2013. So this was a really nice natural experiment because we had the before information and also the drought happened, and now obviously we're looking at the recovery process. So the timing was quite nice for us there. So you'll recall that the summer 2013 drought was said to be one of the worst in 70 years across the country. Now, what we were measuring at the site was a whole suite of different things, including looking at how much water the trees were using and how much carbon they were taking up. So there were lots of different processes being measured at the whole tree scale and leaf scale and all sorts of stuff there. So I can talk more about that, but what I want to do is just go through some of the particular things we were measuring that really responded to drought. And the first of those is the litter fall. So we were collecting the leaves that came down naturally at fortnightly intervals. So we had 24 of these baskets out in the field, and we collected whatever litter fell into those baskets, and then we returned it to the lab and dried it, and then sorted it into the different fractions. So the forest obviously has different species in it, and also there were different things coming down, so the leaves, the twigs, the reproductive material and all those kinds of things. And then obviously we weighed those, and we're up to 3 years worth of data now. But the litter fall showed us that during the drought period, there was a real increase in litter. So this is a paper that's just come out. But what I've got here is the month along here, so I'm showing 2 years on this graph, 2012 and 2013, and those are just the calendar years. 2012 is shown as the closed boxes, the closed circles, and then 2013 is the open one. So the drought is the open circles on this graph, and you can see that there's a really big increase in the litter fall that's happened just as the drought was happening here in 2013. So a huge increase in how much litter was coming down during that year compared to the previous year before the drought. Now, if we looked closely at what that litter composed of, or what fraction that main extra bit was, I won't talk too much about this, but it was the kauri was the main contributor to that increase. And when we looked specifically at what part of kauri it was that was coming down, it was the leaves and also the twigs. So there was a huge increase in the leaf material, and this is a really well-known strategy that plants can use to reduce water loss. Reducing leaf area on the trees really cuts down how much water can get out of the leaf pores, the stomata, during dry periods. So while this is something that's been kind of well established overseas, it had never been measured here as a strategy that the kauri can use during drought to save water in the plant. So the next thing we've been measuring is the water fluxes. The first is the sap flow, and this is how much water is moving up the plant. So we use sensors to measure the xylem movement of water through the xylem, and then we're also looking at the plant water status. So that's looking at understanding what the water stress is of the plant at any particular time. And so these are some of the sensors. Some of the sensors in the tree here, and then these sensors are all joined together with a logger, so we're sampling a number of different trees at the site, and then this is a photo of me taking some measurements with this plant water status instrument. So what we found from looking at this was, first of all, that the kauri, there's really good evidence for the kauri having deep roots. So while some of the literature says they don't have deep roots, in fact they do. And it's quite complicated here, and unfortunately this has come out really small, but what I will say is just to explain it in words. We can see that when we compare the wet summer in 2012 to the dry summer in 2013, there is very little reduction in water use in these trees. So when the soil dries out, if there's not enough water available, the flow of water through the xylem, through the tree, has to decrease because there's just not enough water there. But we know that the trees must be accessing deeper water stores because even when the top soil layers are drier, they're still continuing to use that water. So they must be accessing deeper water, and this is a really good story or a really good outcome in terms of survival of the kauri during dry periods. So deep roots are a really fundamental feature of plants that are able to cope with drought. And this is just showing what the soil moisture looked like during that drought period. So the shaded section there is what the drought was. So the surface layers were definitely getting very dry, but that had very little effect on how much water these trees were using. Now finally, this is the plant water status, and all I want to say here is the fact that the plants were actually able to maintain quite good water status even during that drought period. So they have some mechanisms that allow them to prevent too much water loss. So I won't talk through that figure too much, only to say that that actually shows the evidence. what I want to do is sort of talk a little bit more about the other features. The first is that we have evidence too that root biomass can increase during drought, and this comes from Sarah Wise's work, and she's now a postdoc at Auckland Uni, and she did some shade house experiments on kauri, doing dry down experiments. So these are drought experiments being done in the lab, and she found that, so she looked at 4 weeks, 8 weeks and 12 weeks of drought across there, and this is just a comparison of the droughted and the control plants. And what she found is that the root biomass in the Agathis australis, so in the kauri, was significantly increased by the drought. So this means that the kauri are putting their resources into growing roots in the soil during the drought period. Oh, whoops. And they are, I'm not sure if I did that. It means that they are able to access more water as required. And then the final piece of evidence is stomatal conductance. Now, stomatal conductance is just a measure of how much water is going out of the leaves. And plants have the ability to close their stomata, to close their leaf pores, to reduce water loss. Now, for the kauri, they actually have, we say that they have really tightly controlled stomata. So they respond to low water availability very quickly indeed, and they are known to close their stomata. And these figures are just some measurements that I made at the Arataki Visitor Centre in the Waitakere Ranges on leaves that were on the tree. And what I want to show you here is just the fact that the kauri actually have their maximum water loss happening very early in the day. So many plants will close their stomata late in the afternoon to prevent water loss, but kauri actually close their stomata very early, and this means that they're reducing water loss during the hottest part of the day. So this is really important for them to avoid those air bubbles that I mentioned within the xylem. The evidence that I've got, and the final thing I should say is too, we know that kauri have very large stems and they can store a lot of water in these stems as well, and we're quantifying that as well. So stem water storage is another feature that they have. So in summary, these are all of the different physiological features that the kauri have that allow them to cope with drought. So this is a really good news story for the kauri. Do we need to water kauri during drought? Well, that's a big discussion to have. Maybe we should do that over tea. And I'd just like to say we have a lot of further things going on. We need to quantify when trees get too dry. We need to look at limits to water deficit. We're looking at carbon allocation and how that changes during drought, and more better understanding of internal water stores. I'd just like to finish by acknowledging my funding sources and also all of the helpers that I've had. And thank you for your attention.